Friends, good evening and welcome to the 10th A.P. Mitra Memorial Lecture. I'm Amitabh Sengupta and I shall be the moderator for today's program. Before we begin, may I request all of you, except the speakers for the day, to kindly switch off your cameras and mute your microphones for a smooth conduct of the proceedings. A warm welcome to all of you to our annual A.P. Mitra Memorial Lecture event in the memory of Dr. Ashish Prasad Mitra, one of India's greatest radio scientists. Every year, we organize this event in recognition of Dr. Mitra's significant contributions in this field of radio and space physics. This year, the 10th A.P. Mitra Memorial Lecture is being organized jointly by the NPL Former Scientist Forum, NPL-FSF, the Indian Radio Science Society, InRaSS, and the CSIR National Physical Laboratory, NPL. It will be delivered by Professor Paul Cannon, Space Environment and Radio Engineering Department, University of Birmingham of the United Kingdom. Professor Paul Cannon is a renowned radiophysicist and a leading expert in the fields of ionospheric radio propagation and measurement and real-time modeling of the ionosphere and space weather. We are extremely thankful to him for kindly accepting our invitation despite his very busy schedule. Now, to begin our program, I am glad to inform you that we have always had an unstinted support to our organization from the family of late Dr. A.P. Mitra. This time has been no exception. Traditionally, we begin this program by paying our respects to Dr. Mitra by garlanding his photograph and offering floral tributes. I now invite his daughter, Dr. Patralekha Mitra, more commonly known as Mila, for this part of the program. Mila is a space scientist and a well-known space educator herself. Over to you, Mila. I'd also request you to say a few words after this.
So thank you everyone for joining. I will first please join me in paying a floral tribute to my father.
Mila, you have to turn on the microphone of the photograph. Turn on.
Thank you everyone for joining me in the floral tribute. Since this is now the 10th anniversary of the A.P. Mitra Memorial Lecture, I would like to share a few personal words about him. So his passion for science, you all know about it. He also found tricky ways to bring it into the family and to our lives as kids. He would play mental math games. He would give us challenges like a dare, saying the TV is not working. Do you know how to fix it? So his students would probably have the same experiences of how he made us all interested in science and engineering. He often used to talk about Science City and his passion for, making a science center where students would have interactive science toys to play with and science exhibits. And I didn't really know what he was talking about. Only after he passed away, I was able to visit Science City. And my daughter, who was young, was really excited to stand in the middle of the exhibits and be a part of it. And then I realized that, he was able to take this forward as a founder of Science City. Like Dr. Sengupta mentioned, we are also scientists, and we were amazed that even after retirement, he would remember and know about current research, about the latest papers. And once we asked him, "How do you remember so much about the latest papers and the authors? Because we don't." And he said he has a smart way to filter out the information that is old and keep in the most current and relevant information. So that was a very exciting tip. He also had many other dimensions to him besides his passion for science. He enjoyed travel, and in fact, his friends used to call him Airport Mitra for AP Mitra. For those of you who knew him, you also knew that you might know that he loved reading mystery stories and thrillers. He enjoyed listening to music. He enjoyed food and getting together with friends and students. And I'm very happy that he was able to do all this till even the last day of his life. So, with these thoughts, sharing, I hope I shared a bit more about him as in his personal life with you. And with that, I would like to thank Director NPL, former Scientist Forum, and especially Dr. Sen Gupta for providing the momentum to bring this talk through to the 10th year, the AP Mitra Memorial Lecture. And with that, thank you everyone for joining. And thank you, Professor Cannon, for joining us to give this talk today. And I turn it over back to you, Dr. Sen Gupta.
Thank you very much, Meena, for that wonderful description of some of his uh, passions for science. Uh, May I now invite Mr. R.B. Saxena, who is the Vice President of the NPL Former Scientist Forum, to say a few words about the Former Scientist Forum and also about the Dr. A.P. Mitra Memorial Lecture Series that we have had so far, run in the run-up to the 10th edition today. Dr. R.B. Saxena.
Thank you, Dr. Sen Gupta. Professor Venugopal Achanta, Director CSR NPL. Professor Paul Cannon, Space Environment and Radio Engineering Department, University of Birmingham, UK. Dr. S. Ananthakrishnan, President, Indian Radio Science Society. Dr. Amitabh Sen Gupta, who is the Chairman of AP Mitra Memorial Lecture Committee. Shri N.K. Vadva, who is the Secretary of Former Scientist Forum. Family members of late Dr. A.P. Mitra, NPL Former Scientist Forum colleagues, NPL fraternity, distinguished participants from Indian Radio Science Society and abroad, ladies and gentlemen. On behalf of NPL Former Scientist Forum, I welcome you all to the 10th A.P. Mitra Memorial Lecture today, which is going to be delivered by Professor Paul Cannon, Space Environment and Radio Engineering Department, University of Birmingham, UK, on a new HF over the horizon radar architecture. Speaking about NPL Former Scientist Forum, this is a professional social non-profit organization formed in the year 2003 with well-defined aims and objectives. Forum looks after the interests and welfare of the members in general, related to medical beneficiary cards, assisting for any administrative or pension issues. Forum also organizes scientific lectures, talks of common interest to the members by experts of various fields. In addition, we also organize social activities for our members. In the year 2015, NPL Former Scientist Forum has instituted an annual lecture series in the memory of one of its very distinguished former veterans, the late Professor Dr. A.P. Mitra, FRS, ex-Director NPL and ex-Director General CSIR. This lecture series aims at providing a platform to honor the lifetime contributions of late Dr. A.P. Mitra to radio and atmospheric science in India and on international level. These A.P. Mitra lectures held at CSIR National Physical Laboratory, New Delhi, have been organized jointly by NPL Former Scientist Forum, National Physics Laboratory, and Indian Radio Science Society. The holding of A.P. Mitra Memorial Lecture is proposed to be primarily funded by an endowment fund created out of the contributions from the SY National Organizing Committee for the URSI GA 2005, late Dr. Mrs. Sunanda Mitra, wife of late Dr. A.P. Mitra, Dr. Mitra's family, Dr. K.K. Mahajan, and former students and associates of Dr. A.P. Mitra. Earlier 9 A.P. Mitra memorial lectures, as already told by Professor Dr. Sen Gupta, have been delivered by eminent scientists and researchers of the field of radio atmospheric sciences, viz. Professor Govind Sarup, Dr. Swami Kasturi Rangan, Dr. Shivaji Raha, Professor S. Anantakrishnan, Dr. Archana Bhattacharya, Dr. Anil Bhardwaj, late Dr. Patrika H. Dohati, Dr. Dipankar Banerjee, and Dr. Jayant E.S. Bergman. The 10th A.P. Lecture 2024 is again organized jointly by NPL Former Scientist Forum, Indian Radio Science Society, InRaSS, and CSR NPL as an online webinar. Now we look forward to an enlightening lecture. Thank you.
Thank you very much, Saxena ji. Now to the next part of the program. Friends, in our organization of the A.P. Mitra Memorial Lectures, we have always been fully supported by the CSIR National Physical Laboratory, a place which has been the workplace of Dr. Mitra for close to 5 decades. Before the COVID pandemic period, the A.P. Mitra lectures had traditionally been held at the NPL auditorium. This time, too, the director NPL has kindly provided his full support. He has also kindly agreed to preside over this function. It's now my pleasure to invite Professor Achanta Venugopal, Director, CSIR National Physical Laboratory, to say a few words of welcome. Professor Gopal, please.
Thank you. Thank you. First, thanks a lot from NPL family to Professor Paul Cannon for accepting our invitation and giving this lecture. As Dr. Sen Gupta mentioned, it would have been nice if you could have you in person. We look forward to hosting you sometime in person in New Delhi in NPL. So, but this time, yes, we eagerly look forward to your talk this evening here. Good morning for you. So, just to briefly say, the importance of Dr. Mitra is well known in the Indian context. That is a pioneer who kind of led or activated. He was a catalyst behind the atmospheric sciences studies in the country. Joined, actually, the InRaSS was mentioned here. URSI actually made the matchmaker or played the matchmaker in 1951 when Dr. K S Krishnan, then director of NPL, met him at the URSI Congress, and then he invited Dr. Mitra to come and be the secretary of the then RRC, the Radio Research Committee. In 1954, 3 years later, Dr. Mitra actually came back, joined, and initiated the activities which form one of the pillars. NPL is known now for meteorology, material science, and environmental sciences. The environmental sciences activity was established and strengthened even across the country by Dr. Mitra. So his contributions are remembered through this annual lecture. Is one of the tributes which we can give to the master. So he has done so much of work. One thing I'll briefly say is that the SODAR, in his time, the activity which started, it is still working, and that activity, the data of the ionospheric data is still collected at NPL continues. This is a kind of visionary work which has been done. So not just atmospheric sciences, but upper atmospheric. But he also pioneered in transmission of very low frequency waves, collaborated with ISRO. It's not easy to bring in different stakeholders, and then especially if they are coming from different governmental agencies, like bring them together and then make actually collaborative work was not easy. So he pioneered in that. He's rewarded appropriately with several national awards. He has been the DG of CSIR in addition to being the director of NPL between 1982 and 86. 1986 to 91, he was also the DG of CSIR. So I welcome each one of you. And on behalf of all of us, the past, present, and the future, the students of NPL, we once again thank Professor Paul for accepting the invitation and giving this talk. We really look forward to your talks.
Thank you. Thank you very much, Professor Gopal. We are very grateful to the Indian Radio Science Society, InRaSS, who are partnering in the organization of this event by providing support in some key technical and other aspects. The formation of Indian Radio Science Society, excuse me, was motivated by the pioneering initiatives taken by Dr. Mitra to promote research in radio science in India and in the developing world. It is my pleasure now to invite Professor S. Ananthakrishnan, the President of the Indian Radio Science Society, to say a few words about Dr. A.P. Mitra. Professor Ananthakrishnan has a bad throat, but I hope you are recovered sufficiently. So, Professor Ananthakrishnan.
Yeah, thank you, Amita. Thank you very much for the introduction. On behalf of the Indian Radio Science Society and the NPL Senior Scientist Forum, it is my privilege to welcome you all to the important memorial seminar. My distinguished friend of the last 15-20 years and a past president of URSI, Dr. Paul Cannon, has agreed to give this 10th A.P. Mitra Memorial Lecture on a very interesting topic, namely Over the Horizon Radar at HF. But before we proceed on the same, on behalf of the Indian Radio Science Society, I am honored to briefly talk about late Dr. Ashish Prasad Mitra, the doyen of radio science in India, and whose honor this lecture is being held. Dr. Mitra and I belong to the same alma mater, the Calcutta University, though he was from a much older batch. But since early 1970s, I came to know him closely. Dr. Mitra, while being a president of URSI, initiated the regional facility for radio science of URSI to help India as well as the countries all around India to foster radio science. And that gave us the idea of creating the Indian Radio Science Society about 10 years ago. Dr. Mitra had a very notable career as a scientist and director of National Physical Laboratory, NPL, and as the Director General of CSIR, as Professor Achanta Venugopal mentioned. He also contributed to the initial development of space research in India and was well known globally for his work in radio and atmospheric physics. Dr. Mitra was born in 1927 in Kolkata. A brilliant student all through his educational career, he had stood first in all the major examinations. And after his Master of Science in Physics, he joined Professor Shishir Kumar Mitra, who was a pioneer of ionospheric research in the world since 1930. Younger Mitra's DPhil degree from Calcutta University on this subject at a time was considered the golden era, of Indian ionospheric science, marked the first step of a brilliant scientific career. Dr. Mitra joined the National Physical Laboratory in 1954, and again Dr. Gopal mentioned about it, and soon afterwards set up the Radio Science Division at NPL, marking the beginning of an association that was to last him till the very end. As a successor to his mentor, Professor Mitra, Shishir Mitra, Dr. Mitra carried out ionospheric research program forward at NPL in collaboration with other Indian groups from other labs. Mitra's research topics involved the Earth's near space environment, first with ground-based and later with space-based techniques. As the secretary of the Indian Committee of International Geophysical Year, he steered the Indian program for IGY as well as the International Quiet Solar Year during 1957-58, which pushed Indian efforts into international limelight and ushered in a new era of ionospheric chemistry. His pioneering research in cosmic radio noise for studying the upper atmosphere led to a series of discoveries in atmospheric and solar physics. The 60s saw him working in high-level atmospheric probing with rocket-borne payloads. 70s saw his involvement in developing scientific capability in radar and troposcatter systems. Under his guidance, the SITE experiment with radio beacons led to an India-wide effort on the studies of upper atmosphere. The Indian Middle Atmospheric Program, IMAP, of the 80s saw extensive use of balloons and rockets to carry equipments to ionospheric levels. The 90s saw his initiative with the new world-class efforts, the mesospheric, stratospheric, tropospheric, MST radar, and the SROS ISRO satellite, with specialized capabilities to access substantial parts of the atmospheric environment from near the surface to around 1,000 kilometers for physical properties like electron and ion temperatures, as well as densities at different levels. Around 2000 AD and later, Dr. Mitra had concentrated on global environmental changes arising from human activities and their consequent impact on the biosphere. His contribution to the chemistry of atmosphere and measurement of greenhouse gases in India and to global environmental chemistry, including the measurement of methane emission from paddy fields, were significant. As a leading figure in international programs like the Indian Ocean Experiments, INDO-X, he played a crucial role in the field of global climate change research. Dr. Mitra was the recipient of many coveted honors and awards. He was a fellow not only of all the 3 National Science Academies, but also of some of the most prestigious academies of the world, especially the Royal Society, the Russian Academy of Science, and the Third World Academy. His awards spanned a very wide range and included the Bhatnagar Prize 1968, Raman Award in 1980, FICC Award in 1982, GM Modi Award in 1991, and Meghna Sawa Award in 1992, and the prestigious Padma Bhushan Award of the Government of India in 1987, to name only a few. He was president of the International Radio Science Union for a 3-year term during 1984 to 87. His professional standing notwithstanding, his human qualities such as love for cricket, Rabindra Sangeet, and his enjoyment in fraternizing with fellow colleagues were greatly appreciated by those who knew him, and by the personal anecdotes of his daughter Mila, we came to know a few more things about him. And one of his last acts was an authoritative account of the progress of ionospheric research in India, starting from the pioneering efforts of his mentor, Professor S. Mitra, and duly carried forward by NPL under his dynamic leadership as a chapter in a book entitled India in the World of Physics, Then and Now, in 2007. He passed away in on September 3, 2007, after a month's illness. Only a few months earlier, his 80th birthday had been celebrated at NPL, the institution with which his name has been inseparably associated for the last half a century. He was survived then by his wife Sunanda and 2 daughters, Anusuya and Patralekha or Mila, and their respective families. Mrs. Sunanda Mitra too passed away soon. Our heartfelt homage to both of them. I wish to thank his daughters, especially Mila, and their families, as well as the NPL Retired Science Forum that has initiated these lecture series, and now being organized by the Indian Radio Science Society. Thank you all for your kind attention. Thank you again. Over to Amitabh.
Thank you. Thank you very much, Professor Anand Krishnan, for that very brief, very nice introduction to Dr. A.P. Mitra. Now we are finally ready for the 10th A.P. Mitra Memorial Lecture entitled A New HF Over-the-Horizon Radar Architecture. It will be delivered by an internationally renowned radiophysicist, Professor Paul Cannon. It is my pleasant duty to introduce the speaker for today. Professor Paul Cannon, Order of the British Empire, Fellow of Royal Academy of Engineering, Fellow of URSI, Fellow of IET, Fellow of ISC, member of AGU, is a physicist and an electronics engineer who works at the interface of two disciplines. He is an emeritus professor at the University of Birmingham in the United Kingdom, but has spent most of his working life in government research laboratories and the industry. Since joining the University of Birmingham in 2013, he has been a regular advisor to government departments and science advisors. His leadership of studies and authorship of reports on extreme space weather have guided the development of government policy in both Australia and the United Kingdom. He was elected the Fellow of Royal Academy of Engineering in 2003 and appointed to the Order of the British Empire, OBE, in 2014. Professor Paul Cannon served as the president of the International Union of Radio Science, or URSI, from 2014 till 2017. In 2023, he was awarded the Rower Gold Medal, one of the most prestigious awards of the URSI. Paul has made numerous contributions to radio science and space weather, especially in the fields of ionosphere radio propagation and measurement and real-time modeling of the ionosphere. He is specialized in combining knowledge of radio systems with knowledge of the ionospheric medium and radio propagation to develop new and novel science and engineering solutions. Paul's research has had long-lasting significance on several occasions. For example, his instrumentation has been used operationally by the United Kingdom Armed Forces, and his measurements of the HF propagation channel underpinned the development of the robust HF communication modem standard used throughout the NATO. He now works as co-investigator of the two of the United Kingdom space weather instrumentation, measurement, modeling, and risk projects, and is a co-investigator of a project developing a new over-the-horizon radar architecture based on his patent. So, about which we are going to hear in today's talk. With this brief introduction, I have great pleasure in inviting Professor Paul Cannon to deliver the 10th A.P. Mitra Memorial Lecture. May I request all the rest of you who are logged into the WebEx meeting to kindly switch off your cameras and microphones. Paul, the floor is all yours. We are looking forward to your talk.
There we are. Let's. Can you see my my screen?
Yes.
Right. Good. Thank you. Well, thank you for that introduction. It's lovely to see so many faces I know and some friends there. It's particularly appreciated Anand's description of A.P. Mitra. It's only when you hear of his achievements in such a short, succinct way as Anand presented those achievements that you realise what an amazing person he was. So thank you. I'm frankly deeply honoured to give this 10th A.P. Mitra Memorial Lecture. And this, as you've already heard, is going to be on NOTHR, which stands for Networked Over the Horizon Radar. You'll keep on hearing me refer to this as NOTHR. It's an easy way of saying it. So NOTHR, a new HF Over the Horizon Radar architecture. So my plan for the talk is to introduce the ionosphere, because without the ionosphere, an over-the-horizon radar cannot work. I will then move on to discuss and introduce over-the-horizon radars in a general sense, and this will be quite extensive. And then I will focus down on this networked over-the-horizon radar, NOTHR concept and its benefits. And then I'll finish off by explaining some of the challenges of NOTHR and describe the mitigation strategies for those challenges. So my apologies to those of you whose specialism is the ionosphere. And in fact, my apologies to those of you whose specialism is radar systems, because I'm going to do a fairly superficial presentation in both areas. But I thought it was important to do this because of the, well, certainly to do this for the ionosphere, because it's so integral to a over-the-horizon radar system. So, the ionosphere.
I cannot see the screen. I'm sorry. I can't see the screen. Can you see? Is everybody seeing the screen?
Yeah, we can see the screen. I think it's some problem with your system. Why don't you log out and come back in again?
Okay.
We can all the rest of us can see the screen.
Yeah, please go ahead. Go ahead.
Yeah, you change your layout setting, then it will be visible, I think.
Okay.
Paul,
Right.
please go ahead.
These are I mean, yeah. These web lectures are both wonderful and also a problem, aren't they? Right. Okay. So the ionosphere. So the production of the ionosphere production at mid and low latitudes is almost solely due to solar extreme ultraviolet radiation. And that EUV ionizes the constituent atoms and the molecules. And then in competition with production are the various processes of recombination, which return the ionization to its neutral state. So where we have a balance, then layers form. And you can see in this diagram here that during the day, we might have 4 layers, the D, E, and the F1 and F2, with those F1 and F2 sometimes quite often coalescing into a single F layer. And at night, when we have no production or very little production, then we're just left with the F region, a much simpler ionosphere. So, sorry, I've got a problem here now. Right. So, the ionosphere, as it says here, it varies by day and night, and it also varies with sunspot cycle. You can see some curves on the right-hand side describing this. The higher F region densities will reflect signals at higher frequencies, and the F region is the most useful layer for reflecting over the horizon signals. Problematically, the ionosphere F region varies from day to day for various reasons, and these variations need to be managed in the over-the-horizon radar. And this is one of the most difficult parts about operating an over-the-horizon radar. If there was no variability, it would be relatively easy. So the extreme ultraviolet produced by the sun varies, of course, geographically due to changes in the solar zenith angle. So that affects the level of ionization. Also, of course, at high and low latitudes, the ionosphere is connected or influenced by the magnetosphere above it, and in turn by the sun. And in those regions, the ionosphere is even more variable and may exhibit small-scale irregularities, which cause signal fading. So it's much easier to successfully run an over-the-horizon radar at mid-latitudes. And it's very unusual, I should say, to find an over-the-horizon radar that looks into either the equatorial regions or the high-latitude regions. I should perhaps at this point apologise for the image on the right. You must get fed up with this. So this is you must see so many diagrams which are either UK centric, as this one is, or US centric, but I'm afraid I'm going to ask you to use your imagination and slide the India under this distribution of regions to see the likely effects for India. And certainly, of course, those of you that are steeped in ionospheric knowledge know that India sits right over this equatorial anomaly, which is a challenge for many radio systems. So let's just move on. That's a very brief overview of the ionosphere, just so that we have the words sorted out for those that are not experts in that area. So what is over the horizon radar and how does it work? It's my next few slides. So the first thing to point out that an over the horizon radar is able to monitor surface and airborne targets from around 500 kilometers through to about 3,000 kilometers. So it's a huge distance, and it is actually most often used as a surveillance radar. So in this cartoon here, I have an over the horizon radar transmit and receive facility on the left hand side, and I should say that they are typically 50 to 100 kilometers from each other. And the reason for that is to minimize ground wave self-interference. These radars operate as continuous wave systems. And as a consequence, they would, if they were co-located, they would interfere, the transmitter would interfere with the receiver. They tend to operate round about frequencies between, shall we say, 5 and 25 megahertz. Much lower than most radars, of course. 5 megahertz is probably the bottom limit because the facilities get very large and the atmospheric noise levels go up too high. 25 megahertz is a reasonable estimate of the top frequency, because if we go to too high a frequency, the signals will pass straight through the ionosphere and off into space. There is insufficient ionization in the ionosphere to stop those signals, to refract those signals and bring them back down to Earth. So signals at frequencies below a maximum value are reflected back to Earth. And depending on how high they go into the ionosphere and their path determines where the signals end up. And so in this cartoon here, the orange ray can see a target at quite some distance, whereas the purple-pink ray can see a target closer in. So managing where the radar sees is a big aspect of over the horizon radars. So I just wanted to just give you a feel for how the area of coverage, a typical area of coverage for over the horizon radar. I've just mentioned they can look out to perhaps 500 kilometers to 3,000 kilometers. So this diagram on the right-hand side describes the area of coverage for the so-called JORN, the Gingerley Operational Radar Network in Australia. And this is, as it says in the name, an operational system that's been being used for many years. You can see the so-called BSC at the bottom, which is the operations center. And then you can see radars R1, R2, and R3. And you can see they're all pointing north in some fashion. And you can see with the colored swath there, the area that they can see, they can look. Absolutely enormous region. And with those three radars, the Australians can survey incoming ships and aircraft across the whole of the north coast of Australia, something that would cost an absolute fortune to do with aircraft or space assets. So the potential coverage area of a single over the horizon radar, just to give you a feel, is around about 6 to 12 million square kilometers. The instantaneous footprint lies between a few tens of thousands of square kilometers up to around 1 million square kilometers. And in the next diagram, we will see what I mean by the instantaneous footprint. So here we have a radar, a single radar. There's a transmit facility and a receive facility. And we have a potential area of coverage which could be surveyed by changing the frequency, by adjusting the frequency. But for a specific frequency, there would be a footprint, as is shown there, which is smaller than the potential radar coverage. But as I said in the previous slide, still a huge area. To give you a feel, typically a radar might have a so-called short transmit array, which would be perhaps 140 meters long. I chose that number because it's convenient mathematically. So 140 meters at 15 megahertz typical frequency is 7 lambda. It might have a much longer, or it would have a much longer receiver array, perhaps 2 kilometers long. So that's 100 lambda at 15 megahertz. And of course, the size, the length of that receiver array dictates the angular resolution or the cross-range resolution. Typically, these radars have a resolution of 0.6 degrees, which equates to, at 2,000 kilometers range, around about 20 kilometers. So you don't know precisely where an aircraft is, but you do know within 20 kilometers, and that is quite sufficient to then bring on board an aircraft, for instance, to see what's going on. The transmitter powers for these systems are also enormous. Everything is enormous with these systems. Transmitter power is typically 500 kilowatts. That's lots of RF, and that's lots of, you think of a power amplifier with a 50% efficiency, that requires a megawatt of power to run the transmitter. Lots of power. Right, last I'd now like to just introduce the ideas of radar range and ground range. So the radar range, of course, measures the radar range, or the group range, or the associated with the group delay. Of course, a normal radar would do likewise, but in an HF over the horizon radar, we've got rays which don't go straight from A to B. They go off into the ionosphere, and moreover, they go, because of the ionosphere slowing the propagation of the radio wave, the signals do not travel at the speed of light. So we have to undertake a conversion, a complicated conversion from ground range to radar range. And this process is known as, sorry, I think I said that the wrong way around, from radar range to ground range. And this is a process known as coordinate registration. And in doing that, what we're doing is we're mapping radar range to ground range at a specific operating frequency and for a particular propagation mode. That is a signal that's gone via the E layer or the F layer. To do this, we need to know the ionospheric vertical profile along the path. And that's why I introduced the subject of the ionosphere earlier on. And this could be derived from a model, just a simple, well, not necessarily simple, but from a model. But if we do that, excuse me, the resulting accuracy would be rather poor. So better a combination of model and measurement. And that's what happens in practice. I should perhaps also just mention that the azimuthal direction of arrival and the line of sight speed are determined by reference to that long array at the receive site. I've already mentioned that, but just to say that again, because that's pertinent to our discussions on this new NODA architecture. Everything is relative to the receive site. I'm just going to sidetrack just for a moment and mention the subject of clutter. And I'm going to jump forward in some ways and show you some output from a radar. So I will generally not talk about clutter in this talk, but clutter is the unwanted returns from a radar. And in an over-the-horizon radar, we might have ionospheric clutter, or we might have sea clutter. And clutter, as I say, is unwanted. If we have a look at this diagram here, so we've got range going up the page. We've got several panels, several columns here, and each column relates to a beam. And within any particular column, you can see we've got the Doppler of a target measured with a range of -5 Hertz to +5 Hertz. And the very simple point I want to make here is that if you can see near the zero Doppler line, i.e. a static target, you can see a distinct broadening. If this was just a radar that was looking at a smooth Earth, it would see just a simple line there at zero. But we see this broadening. And in this case, this is due to reflection from the sea waves scattering the signal. And in fact, quite often we see a line either side of the zero Doppler line, and that's a Bragg scattering line. But the problem with all of this is it means it hides the target. And you can see on the expanded diagram on the right, there is a target there. You'd hardly know it. But that target has nearly been obscured by the clutter. And indeed, if it had been going a little slower, it would have been obscured and we'd never have known it was there. And I should have pointed out that 1 Hertz is a target going at 36 kilometers an hour for some from settings that I'm going to explain to you later on. So you can see clutter is a real hindrance. So I'd just like to show you these couple of diagrams because personally I find it nice to understand what the technology looks like, and there's lots of heavy engineering in all of this. On the left-hand side, we have a receive array in Canada, actually, and it's an array of vertical monopoles. That's quite common. This is a 2-dimensional array, and you can see them going off into the distance. So many antennas have to be maintained, kept in phase, all of those things. And then on the right-hand side, we have the JORN, the Jindalee Operational Radar Network transmitter array at one of its sites. And this is an array of vertical log periodic antennas. Again, substantial piece of engineering. Right, well, any radar, of course, has to, you worry about the resolution of the radar, ambiguity relationships, etc. And I've got a bunch of equations here, which I'm not going to go through, but I'm going to, but in the next slide, I will use them. But you can see that we have to worry about the chirp bandwidth, which is B, the pulse length, which is T sub P, with its equivalent repetition frequency of F sub P. We normally integrate these the signals. I have a number of pulses, and we have to be cognizant of the carrier frequency. So let's have a look. Let us have a waveform, which we choose a waveform which is a chirp. So an FMCW system chirping over 10 kilohertz. Let's have a pulse length of 20 milliseconds. I should say all of these numbers are typical. A PRF, that's a PRF of 50 hertz. Let's integrate over a second. And let's have a carrier frequency of 15 megahertz. And now you can see that if you look at the group radar range, you can see that the resolution is about 15 kilometers in range. Remember I said earlier on we had a cross-range resolution of about 20 kilometers, so they're matched. And we're able to measure the target velocity to the nearest 36 kilometers per hour. Notice also that we can see the radar range, we have an ambiguity out to 3,000 kilometers. So without changing the waveform, we can look without ambiguity out to 3,000 kilometers, or we can measure even fast targets traveling at 900 kilometers per hour. So these are just these are typical settings for an over-horizon radar. So again, at any radar, you would you have to worry about the signal to noise ratio. And here's the appropriate equation for a over the horizon radar. It's pretty similar to the equation that you would derive for a microwave radar. It's just been set up slightly differently for convenience. But our output signal to noise ratio after compression is of course higher if we've got a large transmitter power, high transmitter gain, high receive gain, and it is dependent upon the radar cross-section and the coherent integration time. Equally well, the signal to noise ratio reduces by lambda squared. We've got to worry about all the losses. This is the losses from transmitter to target and then back to the receiver again. We have implementation losses, of course, and we have to worry about the noise. We find that it's most useful not to look at it this way as a signal to noise ratio, but better to look at it in terms of the minimum detectable radar cross section. So here that previous equation has been reorganized and set dependent upon the minimum detectable radar cross section, the MDRCS, and essentially the equation is turned upside down. So we can use this and we can look over a region of interest and we can plug in all of the parameters here for a hypothetical radar, and we can see what radar cross-section target can we see? How small a target can we see? So, but then to do that, it's meaningless if we have no idea what the typical radar cross-sections of a target are. So radar cross-sections in this area are typically modeled using the National Electromagnetic Code, which is essentially a kind of, you set up a wire grid approximation to the target, and then you can calculate the nominal RCS. So the number I'm going to ask you to remember is this airborne target commercial airliner, which has a radar cross-section of 20 to 30 dBm squared. But you can see as you go to smaller targets, airborne targets, the numbers get smaller. You know, a missile is smaller than a fighter-sized aircraft, which is smaller than a commercial airliner. And if you look at surface targets, then you can see the cargo freighter will have a larger cross-section than the commercial airliner because it can be huge, but a patrol boat will be smaller and a fast boat will be smaller still. So, but probably best if you can just remember the 20 to 30 dBm squared, that's useful. So I'm set, well, we could have a hypothetical radar and we could calculate the MDRCS over a region. So let's do that. let's explore the area of coverage for a hypothetical conventional radar, which is what we're talking about here, which we're going to place in the southwest of the United Kingdom. It's going to look out over the Atlantic Ocean. And we're going to configure it with 8 transmit antennas and 96 receive antennas. Now, that is substantially smaller than an operational system. But we think that this is the largest array that a university could aspire to build. And we are, we might one day have the opportunity to build one of these, or we hope we will. I'm going to dimension this with 192 kilowatts transmitted power in total. That's a funny number. And when we start talking about the novel architecture, it will become clear why I've chosen 192 kilowatts. But I'm going to show you the area of coverage for this conventional radar, and then later on I'm going to show you the area of coverage for a novel architecture radar, and I want to be able to do a fair comparison. So, as I say at the bottom, what targets would a radar of this type be sensitive to? And here we have an MDRCS conventional configuration plot on the left, and the corresponding optimum frequency on the right. I'll come back to the optimum frequency in a moment. So I'm not sure whether you can see my cursor, but we'll try. You can see this red cross here, the south of the UK, and that is where we have a transmit and receive facility separated by the order of 50 kilometers, so that there isn't any, there isn't substantial amounts of interference. And you can see that in the the first dashed line here is at 500 kilometers range. You can see that the typical minimum detectable radar crash section is of the order of 10 to 15 dB meters squared. And so that would suggest that this radar could see a commercial airliner. And then at the far extremes, it's probably of the order of about 25 dB meters squared, which suggests that even at the far extremes, this is the second dashed line is 1,000 kilometers. It suggests that even at the far extent of the range here, the radar could see commercial airliner. I add the picture on the right-hand side here just out of interest. That you can see it shows the optimum frequency on the particular day that this calculation was done for. So we have to specify the sunspot numbers and the other characteristics of the ionosphere, and particularly, of course, the date and time. And you can see that close in, the best frequency would probably be down around about 13 megahertz, and further away, it's probably up at about 18 or 19 megahertz. Okay. So this is all sort of still trying to fill in lots of background about over-the-horizon radars and provide some appreciation of how complicated over-the-horizon radars are, and the problems that we have just running even a conventional radar. And all, or if not most probably all of these considerations apply to the novel networked over-the-horizon radar, but there's some other issues as well. So let's supposing we built one of these radars and we want to use it and we want to look out at about 2,000 kilometers range. So what frequency do we choose? And the way we do that is we have a small radar which actually benefits from the reflections, the scattered signals from the ground or the sea. And this small radar, but it's not looking particularly for targets. As I say, it's a small radar, and it transmits signals in a frequency range here. It's shown from 10 to 30 megahertz. The signals travel out, they hit the ground, they reflected back, and the power of the reflected signal is shown in this diagram on the right-hand side. And this gives us a feel for the frequency that we should use to operate the radar. So as I say, let's choose 2,000 kilometers range. If we go for 2,000 kilometers range and we want to pick a strong signal, which is in yellow, we probably would choose a frequency at about 19 megahertz, because that would give us a good signal. We probably we wouldn't choose, for instance, 11 megahertz, because the signal strength would be, you can see in the blue there, and that would be a smaller signal. So that is how frequency management is achieved with these over-the-horizon radars, how we choose the right frequency to make a measurement. So associated with with frequency management is the subject of coordinate registration, and I briefly mentioned that earlier on. So if we know the operating frequency and the mode of operation, ERF, to do coordinate registration, we need ray tracing. At the bottom here, you can see some ray tracing. You can see it's based on a model of the ionosphere, and whoops, oh dear, sorry. And it's based on a model with, in this case, but it could be model with additional data. And we launch a series, a so-called ray fan, a series of rays from a low angle to a high angle. And you can see in this case, some of the rays, the first ray, the lowest angle, travels up to the E region and then comes back down again. So it's got reflected around about 110 kilometers. Whereas a higher angle ray went propagated up into the F region at maybe 250 kilometers. And so if we know the operating frequency and we know the mode, we ray trace through an ionospheric model, it will provide us with a range of rays for the different elevations, and they will propagate out to different distances. Now, if the model ionosphere is perfect, perfect representation of truth, one of these will correspond to the measured radar range. So imagine you run a radar and it tells you what the radar range is. You can then associate that range of that azimuth with this ray trace, and that will give you the ground range, and that is the essence of a radar, over the horizon radar. All of the explanation I've been giving you so far has been to get us to this point to do that coordinate registration and know where the target is. And as you can see, it's really quite difficult to do. Of course, if the model ionosphere isn't perfect, then there'll be a coordinate registration error, and that's a whole new story. So, after all of that introduction, but it was deliberately long, I guess, onto networked over-the-horizon radar. I want to point out to you that this is research in progress. Well, we'll see how we go. I should also probably point out that this is based on a patent that we hold of this concept, which in itself draws on Australian DSTG, their Defence Labs intellectual property. So here we are with a diagram that looks remarkably similar to one that you saw earlier on. So in this case, again, we have a transmitter and the signal goes up into the ionosphere. It's reflected down to a aircraft. Signal gets reflected or scattered back to a receiver. But note that the transmitter and the receiver are not now 50 kilometers apart. They're actually around, well, I don't know quite what this is. They're 300 kilometers, shall we say, apart. There's a difference between the southwest of the UK and the Sea of Belgium, I would guess. They are, so we have, this is completely different. And in fact, if you think about it, this is not a pseudo monostatic case, which is what we had before. It's actually clearly a bistatic configuration. And then once you make that leap, then it's easy to say, well, let's have not just one bistatic receiver, but let's have two bistatic receivers, 3, 4, 5, if that's what you want. But you know, and you could do that in principle with a conventional over-the-horizon radar. But the problem is, with a conventional over-the-horizon radar, that receiver array is enormous. It's 2 kilometers long, and 2 kilometers means it's really expensive. Whereas in this configuration that we're talking about now, this NODA configuration, we're talking about having one transmitter and multiple receivers, and all the transmitter is the long array and the receiver is a short array. And although it's actually not sensible to have one single antenna, I hope I'm going to show you in a moment that you could have one single antenna in principle and still form beams, which sounds like magic. But the trouble is, like all magic, there's a catch. So now the other important point is one that I've already alluded to, and that is that the transmitter here is going to have very long, going to be very long, and the receiver array is going to be short, and that is in contrast to a conventional array. Remember, a conventional array had a small transmit array and a long receiver array. We're doing the opposite here. So that was slightly out of order there. I hope you understand that. So, but maybe I'll say it again in this diagram here. So the key characteristics of NODA here are a large transmit array and many small receiver arrays. And indeed, as well as many bistatic receiver arrays, we could have a pseudo-monostatic array. Okay, this is in contrast to a conventional array. So how is it that you can synthesize beams at the receive stations if you've only got a very small array? And the answer is that you transmit orthogonal coded signals on each of the transmit array elements to distinguish the signals on one antenna from the signals on another. And then if you do that, you can get that azimuthal discrimination. So that's the magic bit. As I say, I'm going to show you all the problems in a minute this brings to bear. So let's let's look at this and just go through that process of orthogonal coding again. So we have this diagram on the right. We have an array of on the left-hand side of a long array of antennas, and they're radiating an aircraft, and then the signals are picked up on one receiver or another receiver. There's two receivers shown in this case, and the beamforming is done at the receiver for the transmitter. So I'll run through that more slowly. So we assume a long multi-element transmit array, and we transmit a set of orthogonal waveforms, one per array element, and we defer the transmit beamforming until after we've had propagation, scattering from the target, and propagation again, back to the receiver. Then we do the transmit array beamforming at the receive system, knowing the transmitted coded signals and the transmit antenna geometry, of course. And if we do that, it gives us the target azimuthal direction of departure. So we've now got we've got the receiver calculating the beam that the target falls into, but that's all reference to the long transmit array. As I say, magic. Let's just run through the benefits, and there are lots, and that's why this is interesting. So I've already mentioned receive systems are small, they're physically simple. We don't have such big engineering. Therefore, radar receive systems are relocatable. You could even argue they're mobile. I won't, but you could even possibly. You could have receive systems can be numerous because they're small and they're simple and they're cheap. And they can then, if you've got numerous receive systems, they can cooperatively measure velocity instead of just speed. If you think about it, a single over-the-horizon radar can only give you the line of sight speed. An interesting one is that the receive look angles will vary for different receive systems, and consequently the radar systems can detect targets hidden in clutter, in C clutter, because the clutter tends to be worse from certain directions relative to the relative to the wave directions. And actually, it can also detect targets tracking perpendicular to the monostatic line of sight. So, you know, if you've got even a fast target that's moving perpendicular to the line of sight of a monostatic radar, then of course it looks like a slow target and it gets lost in that C cluster. And in fact, finally, I should also say that if you have a 2D antenna, and you saw that for that Canadian receive system, you have that, and it's either the transmit system or the receive system or both. You can steer nulls, and if you can steer nulls, it means you can minimize the clutter, which is extremely important and beneficial. Right, well, I said there were some problems, and we're going to run through, I think it's maybe 4 problems, see the consequences and hopefully overcome those consequences, at least on paper. So if you've got a noise limited system, and all of our calculations have been based upon noise limited, but not cluster limited. If you have the aggregation of M matched filters, so we've now got, we have at the transmitter, we have M antennas with M codes. We'll need M matched filters at the receiving system to distinguish the signals from each of those antennas, and then to synthesize the beam. that will give us a performance degradation because you're basically adding noise in. There's an uncertainty associated with each of those match filters. And unfortunately, that's a big number. So if you've got M antennas or M codes, then you end up with it is directly proportional in a linear way to the number of those codes. So if we have 100 transmit array elements, the whole system, this whole NOVA approach, will be 20 dBs less sensitive than a conventional system, unless we can find some ways to mitigate this. Because, if it's 20 dBs less, we really aren't going to find another factor of 100 of transmit power. Remember I said we were already going to draw 1 megawatt from the grid to run this radar. We're not going to run 100 megawatts, take 100 megawatts from the grid, and all the other problems that come with it. So, this becomes a non-starter. Now, that's probably an exaggeration. There are, but it becomes a real challenge unless we can find ways around this. And luckily, there are ways. So, first of all, that's where it sits in that equation. We're going to put that extra factor of NM in there, which will increase the minimum detectable radar cross-section. So I would like, first of all, before I do talk about mitigations, to just take you through one of those area coverage map diagrams. I mean, if you consider now a hypothetical NOVA radar, which is the reverse of the conventional configuration we've already discussed. So now we've got 96 transmit antennas, and we've got 8 receive antennas. That's the other way around from before. And we're going to have them each radiating 2 kilowatts, and that makes a total of 192 kilowatts. That is why I came up with that crazy number earlier on for the previous calculation. And this time we're also going to consider the case of a monostatic receiver and 2 bistatic receivers. We get this. So on the right-hand side is the diagram for the conventional radar, which you've already seen. And on the left, and it's unfortunately got a different color scale. So you can see the situation for another radar. Now I need to take you through this a little bit a little slowly. So let's look at the top left image. RXM stands for receiver monostatic. So we have a transmitter and we have a receiver right next door to it. So it's a monostatic configuration. It's pretty much as close to conventional radar as we could get, but we've swapped around the transmit array and the receive array. And this is the area of coverage that we get. And you can see that because of this sensitivity reduction due to the noise, or due to the match filters, we end up with a much lower MDRCS threshold. So typically, close range, we're down now at 25 to 30. 25 to 30 dB meter squared. So we can just about see that commercial airline, but we've got nothing, and we've got nothing to spare. And at distance, we really don't have a chance. But you can see it looks pretty much like the conventional radar map. If we have another receiver, so we have a bistatic configuration, and that is the one that's just off the coast of northern Spain, then we get something similar. And if we do another one, we have a receiver which is located out in the Atlantic, then we get the same again. In each case, you can see the so-called skip region, for those familiar with that concept. What we've also done is we've said, well, what happens if we if we require 2 receivers to be able to see the target at any one time, what does the footprint look like? So let's not worry too much about sensitivity, let's worry about the footprint. And if we do that, you can see that the footprint fills in to look very much like the conventional coverage, except of course the sensitivity has been reduced. So at some levels we're quite happy with this because it indicates that using these different systems cooperatively, a bistatic radar will work, but of course we have the sensitivity reduction. So what are we going to do about it? So there are many mitigations, and we're pretty confident that we can deal with this. So what the first one is that actually we will have a small directional receive array. So it won't be a single antenna, it'll be a small directional array. And that's able to steer nulls onto atmospheric noise sources and interference, and that will improve the signal to noise ratio or improve the MDRCS. Interestingly, we believe that we'll be able to give longer integration times, which will improve signal to noise ratio. And that's possible because we can stare at a surface region, at a surveillance region continuously. So a conventional radar tends to have to manage its resources by multiplexing between different tasks. But for us in this architecture, if you think about it carefully, the only limitation is the level of parallelization in the processing that we have at the receive system. The longer integration times may also make it possible for us to use a combined tracker and coordinate registration system. And we believe we'll get a few more dBs of benefit there. And then finally, and possibly actually really quite an important enhancement, we will be able to have cooperative detection and tracking between the receivers, which will enhance the performance. So we're pretty confident that we can win back that 20 dBs that we've lost in sensitivity by moving to this architecture. So we're hoping that we'll be able to get the benefit of NOVA and deal with the penalty of the NOVA architecture. But unfortunately, there are 2 or 3 other problems. One interesting one, if you're interested in RF engineering, is that because we've got out-of-phase orthogonal signals on the transmitter antennas, there's a significant transmit mismatch occurs. And this is due to mutual coupling. We've got signals that are out of phase between adjacent antennas, and they're feeding one into the other and the other back into the first. And the consequence is that the VSWR goes up, and it goes up quite badly. But it does actually get a lot better if you can separate the antennas by more than half a wavelength. So what we're doing is, or proposing to do, is to separate the antennas by more than half a wavelength, but then we'll get grating lobes, but we're going to control the grating lobes with the receiver array. Another challenge is that the NOVA coordinate registration requires knowledge of the ionosphere of bistatic paths, not just a monostatic path. So if you think about a conventional radar, the signal goes out from the site, it goes off to the target, and it comes back more or less to the same place. It's 50 to 100 kilometers away, but it's more or less the same place. So you only have to understand the ionosphere over a very narrow, very narrow azimuth range. But in our case here for this NOVA architecture, we will need to know the data over a the ionosphere over a very large range to a common, range of azimuths, and well, a very wide range of latitude and longitudes for us able to specify the ionosphere to account for that ionosphere and apply it to a bistatic configuration. We believe that modern assimilative ionospheric models, which they optimally combine data from many sensors into a background model, is the way to deal with this. That is a technique that is essentially being used in weather forecasting now, and has been adapted to the ionospheric modeling. And in fact, you can, this picture on the right purports to show or does show data from all those crosses are data sources, which can be used to update a background model to make it both real-time and optimal. And that's an important step. And then I think this is fine. Our final problem. Waveform modeling suggests that if we want to stick to the radar parameters that we discussed earlier on, it'll actually, with the ionosphere being what it is, it'll be difficult to maintain waveform orthogonality for more than 50 waveforms. So we can't actually have a 200 elements transmit array anyway. We'd actually need to cut that down because we can't actually, as I say, maintain 200 waveforms, separate orthogonal waveforms in the system. We can only have 50. So we have a strategy, we believe, using subarrays. And again, we'll end up, if you do that with grazing loads, but again, we can use the receiver array. So that's about it. It's really a very fast canter through both conventional over-the-horizon radars, and I hope that you've managed to pick up the essence of how they operate and how we hope to develop this networked over-the-horizon radar. So, in summary, we believe that the Nodder concept has a number of advantages over a conventional radar, and that includes small deployable receive systems, an inherent capability to detect slow targets which would be hidden in the cluster of a conventional radar, and an inherent ability to measure velocity as opposed to line of sight speed. However, it's a technical challenge to implement, and that's going to require mitigation of the sensitivity reduction for a noise rather than cluster limited system, 3D real-time ionospheric modeling, which is another challenge, and a limited number of waveforms, and that's a third challenge, but all tractable, we believe. As I say here, fortunately, it seems that the Nodder architecture is very flexible and it can be adapted to overcome the challenges. And actually, fortunately, and perhaps this is why we are actually looking at, partly at least why we're looking at this, this technology could not have been contemplated 5 years ago. It requires a significant amount of digital signal processing in the radar and a significant amount of processing in the ionospheric modeling to make it work. I think that's it. Thank you.
Well, thank you very much, Paul, for that wonderful lecture. I think you've talked about essentially a concept called the over-the-horizon radar, which provides very wide area surveillance options, particularly for moving targets such as the aircrafts and ships. Well, not so much for ships because they're slow moving. You've also talked about a new architecture that has been proposed by you, the Nodder concept, network over-the-horizon radars, which consist of large antenna arrays and relatively short receive arrays, but a number of them networked together. So you've talked about multiple benefits of the networked concept and of course the associated challenges, and you've described strategies to mitigate each one of those challenges. So essentially, that's been the talk, and I'm sure there'll be several questions in the audience based on your talk. I myself have a few, but I'm going to just wait till the others have asked. So if anyone has a question, can you please unmute yourself, switch on your camera. Prashant, please go ahead.
Yeah, thank you, Professor Cannon, for the interesting talk. My question is with regard to your bistatic and the monostatic configurations you're talking about. So I was wondering how critical the positioning of these receivers as well as the ground separation is going to be critical. The other thing is, so what are the criticalities in terms of the time synchronization between these receivers for the effective detecting the targets?
So I don't believe the I don't believe that it's critical where those bistatic receivers go. I think inevitably, sometimes the ionosphere will not support signals, and on a particular frequency, it won't support signals from transmitter to target to, shall we, 3, 4, 5 receivers, bistatic receivers. It just won't work. I mean, if you imagine there was a terminator going through the region of interest, obviously, you know, that wouldn't work. So the whole concept it works better if there are a number of receivers, you know, not just, well, certainly not just 2. 3, we seem to show, for the conditions we were looking at, it seemed to show that 3 was fine, but 4 or 5 provides some level of redundancy. Sorry, what was the second part? I beg your pardon, sorry, Hon.
The synchronization between...
Synchronization. Yeah, actually, that's a really interesting one, which we've sort of we've brushed under the carpet at the moment. So GPS does, or GNSS timing does, you know, a lot for us. So we will certainly need we'll need good timing synchronization across the network. I mean, that's undeniably true. The bit we've sort of brushed under the carpet because it's really interesting, but we don't have the resource to look at it, is how plausible is it to not just process the data incoherently from multiple receive stations, but could you, in principle, deal with it coherently from multiple receive stations? I mean, then of course you'd need you'd need very good synchronization, and I mean, but probably the overriding limitation there will be the instability of the ionosphere, because the ionosphere is a pretty unstable medium. So whether we could actually ever conceive of bringing everything together coherently, I don't know. We would need very good synchronization for that. But I'm not too worried. You know, the usual scientific answer to your question is GNSS, and I think it really will work in this case. Don't forget, our waveforms are we're only working with a 50 Hertz PRF. You know, it's not like working at microwave frequencies with a very fast PRF.
Thank you. We have several other raised hands, but let's just take Yashwant. Yashwant, please go ahead. Unmute yourself.
Yeah, thank you. Thank you, Professor Cannon, for a very interesting lecture. I had a couple of questions. One was this number M, that is the number of elements and therefore the number of orthogonal codes. I guess there must be a way to optimize that, because there's probably reasons to increase it, but there are also degradation of the performance as you make it too large, right? Because of the noise from the match filter.
Yeah.
So I guess, and is there a clear way to optimize that, or what does it depend upon? And my second question was about the long integration time. So you said since staring at the same region, you can integrate long, but there must be a upper limit, because it's not looking at a static scenario, it's looking at a dynamic scenario. So do you run into a regime where the integration cannot be too long?
Yeah. Yes. I mean, optimizing the yes. I mean, the simple answer is in both cases I agree with both of your questions, and I mean, I'm sure there is an optimum value for the number of waveforms we use, and there will be a limitation on the number on the length we can coherently integrate for. When I said I thought we could overcome the losses or the sensitivity degradation in the system, shouldn't call it loss, sensitivity degradation, it was on the basis of a very conservative estimate of benefit from each of those benefits. But yeah, it's research in progress. That's a terrible answer, but it is research in progress. We really don't know. I mean, I thought it would be nice to kind of, well, I hope it has been nice to listen to something about which is quite conventional and well known, well understood, and then tell you about things that we're fighting our way through at the moment. So yeah, and I think both really good questions that I don't know the answer to, but they are on the list of things we do need to worry about.
Thank you. We have several other raised hands. Professor Gopal would like to ask a question. Please go ahead. Professor Achanta.
Sorry, I was saying we will give chance to others. Like I have similar questions. Like it's more of, I mean, the challenges seems to be plenty. There's a lot of modeling needed. So I think Professor Paul has already mentioned that. So I think my question was more about if you have multiple sources, would there be any way you're looking at using different frequencies?
Yeah. Sorry. I think I lost one word in there. So, are we looking at different frequencies? Sorry, what the sentence before that was? Could you repeat it?
Basically, with different sources.
Yeah.
Are you also looking at using each one emitting at different frequencies?
Right. Yes. No. Right. So, if I'm understanding that question correctly, could each of the the receiving stations be operating on a different frequency? So for argument's sake, could you transmit signals on 10 megahertz with the view to the signals being scattered through to one receiver, and 15 megahertz with them being scattered through to another receiver? Is that your question?
Yes.
Yeah, and the answer is we believe we can. We would. We'd try. We would. I mean, the obvious the place to start would be to operate on the same frequency. But yeah, we think that we would like to look at the whole idea of multiplexing different frequencies, But I mean, we wouldn't simultaneously transmit the same signals on two frequencies because, well, then we're running enormous powers, even if we had 2 kilowatts per antenna, two frequencies at the same time would suggest we have to back off the drives, otherwise we'll end up with lots of intermod. So, there are practical problems along with what would be ideal. So practical problems will constrain us. But yeah, yes, another really good question. Yep.
Thank you. Janardhan, Professor Janardhan has a question. Jerry, please go ahead.
Thank you,
yourself.
Dr. Cannon, for a nice talk. This background noise, you'll have to forgive until I finish my question. You spoke in the beginning of your talk about clutter, the C clutter, and you showed a target sitting very next to that noise. I mean, if it's sitting within that, you're completely blind to it?
I'm just trying to think whether I would agree that you're completely blind to it. Yes, I think you are completely blind, certainly with a conventional radar. I mean, you know, the great thing about this configuration, as I said, that with this nother, is that we can steer the beams. So, you know, as soon as we've got a two-dimensional radar, two-dimensional antenna at one end or the other or both, we can steer the beams. And quite often, you know, the radar, I'm trying to think, let's give you a good example. If we, you know, we were looking, we were looking towards, I can't think of a good one at the moment, but you know, basically we would end up, we would be able to steer the beams to mitigate the clutter. Oh, actually, possibly a really good example is that we're looking at a target, and we're using an E mode, but the cluster's coming from on an F mode. Or we're looking at a 1F, but the cluster's coming in on a 2F, because, you know, and then you would steer a null so that you can't see the cluster coming in from on that 2F mode. And you know, then that would give you the opportunity to see that target on the 1F mode.
Great.
That makes sense.
Thank you. We have several others. Animesh Mitra, Professor Animesh Mitra. Animesh, please go ahead. Unmute yourself first.
Okay. Thank you. Am I audible?
Yes, you are. Please go ahead.
Thank you, Professor Cannon, for your excellent talk. Now, I have a question, actually, which is already asked to an extent. That means you, at the beginning, you mentioned that 5 to 25 megahertz frequency range is mainly used. So, in your discussion, you did not mention specifically at which frequency you'll be using. So, is it adaptable frequency? That means depending on the atmospheric condition, we use certain frequency, which is performing in the best way. This is my first question. And second question is that main advantage of over the horizon data is that it can detect the target from a very long distance, which is not possible with normal kind of radar operating at micro frequency, that is 3,000 kilometers. But here question is that whether there will be any issue of the target identification. That means, is it possible to identify the target with certainty, or measure the velocity of the target with the certainty that we can achieve with the normal radar? So this is my second question. Third question is that whether in future it would be possible to use this kind of over-the-horizon radar in equatorial region with the improvement of the atmospheric model and building up the adaptable network system. So that these are my
yeah, okay. Actually, so it's slightly, I don't know why it's slightly distorted on your line. The first part of that I got, and then I'm having trouble with the second part, all the details of the second part of your question. So the first part you asked whether whether we would vary the frequency, and the answer to that is definitely yes. So over-the-horizon radars are, I'm going to say they're frequency agile. That's not that makes it seem like they can change frequency quickly, but they're always set up so that the frequency can be varied, and that becomes, I mean, that's a huge challenge because you've got to build an antenna that's wide band, and that's both transmit and receive antennas, but particularly the transmit antenna has to be wide band. They're typically, and then the antennas might, I think John has two sets of antennas, low band and high band, and to make their life slightly easier. But yes, you can change frequency. You change frequency partly because you want to place your power in the you want the power to go in the place you want it to go to. You want it to go, look at a particular area. But sometimes you change frequency because there's another user on that frequency. And of course, when you're running such enormous powers, then it's not a very social thing to do, to be running these huge EIRPs on the same frequency as some other user. Right, so I got that bit. I'm so sorry, and I couldn't. The odd word would disappear.
My second question was very quickly. Can you hear me now?
Well, I can, but it's slightly distorted. That's the problem. Yes, yeah. I don't know why.
Okay. Can you hear me now?
That's pretty good. Let's try.
Okay. My second question was quickly that whether there is any issue with the target detection. Target.
I think what Animesh is talking about is because of the uncertainty of the ionospheric profiles, the target detection, your
suppose this is a
conversion from the actual range to the ground range. Conversion brings in a lot of uncertainty.
I've got you. Yes, right. Okay, thank you. Sorry. Yes, so there is. I mean, over-the-horizon radars always have. If we go back 30 years, or maybe even longer, the earlier over-the-horizon radars all particularly had problems with the coordinate registration. More recently, the ionospheric models have got better, but with this another architecture, we're asking for another layer of fidelity, another level of fidelity that normal radars don't need, because we are trying to cooperatively. Well, the first thing is we've got a bistatic path, so we need to actually look over a wider area. And then, of course, if we've got two receivers and they're both receiving signals from the same target, if our ionospheric model is slightly wrong, we'll see not just they won't see the same target in the same. They won't see one target in the same place. They'll see one target in two places because the ionospheric model for one is perhaps wrong and the ionospheric model for the other is right. So, we have to bring that together. So there's been some very nice work done in America in this sort of area, and we're looking at that and how we can adapt that to this particular architecture. So I'm sorry, you lose the old word.
Okay, thank you.
It's so difficult.
I think given that
I'm done.
there are several others that are waiting to ask questions on this, may we take your question later? You could perhaps write to him separately. Dr. Pallam Raju has a question. Dr. Raju, please go ahead. Unmute yourself.
Yes, am I audible now?
Yes, absolutely.
Yeah, first of all, thank you, Paul, for a fascinating talk. It's really interesting to know the various aspects of this over the horizon radar. But we understand that the 3D ionospheric characterization is something which is a bedrock beyond which probably or it's an underlining important thing that we need to know beyond which this is possible. And as a ionospheric physicist, I'm just thinking if you have another configuration of a receiver farther away, wherein you get there is a bistatic mode wherein a transmitter, the beam goes and it's received in the farther away, and then there is a target which, as you showed in the diagram, there is a plane moving, it's reflected back. So probably can the combination of these two be used to really identify the target better, and in the same time help us in studying the ionospheric physics also?
Yeah, so right, so an absolutely critical part of this is the ionospheric modeling. So I will be flippant, but much of this is just engineering, and that's not fair, because I'm some days I'm an engineer and some days I'm a scientist. So I'm not being rude to engineering, but there are a lot of this requires engineering solutions. There's some very difficult engineering, but one of the critical issues is getting this ionospheric model correct. That said, there are ways, a conventional radar, for instance, can geolocate. It can work out where the target is with reference to reflections from coastlines, for instance. So you imagine the radar is looking at a certain area, and the aircraft that it's looking at is near a coastline. The operators can see the coastline because there's the backscatter that changes. There's a change in the between sea and land. So if the aircraft that they're looking at is near that, you've got an independent measure that doesn't really matter. It doesn't. You don't need to know too much about the ionosphere to be able to make that work. So it's ionospheric agnostic. But yeah, if we can't make the ionosphere work in this, then the scheme would have to wait for another few years of development. I mean, again, I mentioned the fact that that only now is it possible to build a radar like this because signal processing has become so powerful. But only now, as I said, is it possible to do this, because only now have we got ionospheric models which have any hope of providing the fidelity that we need. And I certainly wouldn't want to do this off the coast of India, for instance. I mean, where you've got to deal with the equatorial anomaly, and I certainly wouldn't want to use this looking up into the Arctic. So it's it's all a challenge. We're starting at mid latitudes in our thinking, because that's the only that's tractable.
Thank you. We have one more question by Professor Anand Krishnan. Anand, please go ahead. Unmute yourself.
Paul, thanks. Thanks a lot for that. Very insightful lecture. My question is very purely selfish. It is that when you transmit at 5 to 25 megahertz, you're polluting the radio astronomy skies.
Yeah.
So, but it is not all bad, in the sense that one is looking at the sky and it is not visible; it is opaque. But nevertheless, the enormous amount of power that you transmit is going to get to the moon. And so even if you had put a low frequency receiver in the moon, this kind of, you are not the you won't be the only one, but there'll be lots of people who are transmitting, and they're all adding up.
Yeah.
And so the pollution on the moon, even for frequencies below 30 megahertz, is significantly increasing in the last 20 years.
Okay. Yes.
So I don't think there is an answer to that. But
I don't know what to say really. I mean, I agree with you, and I would in many ways. Well, no, I'd certainly like to avoid it. I mean, we are being very good. I mean, we are. You know, we're planning lots of filtering for. You know, because you can imagine we've kind of we've bought one or two transmitters just to see what we can do, and check filtering out, and we're kind of doing various bits of de-risking, and I mean we are desperately trying to keep the radiation down. It's one reason why I don't want to put two signals through one PA, and then we've got all those mixing products. We're trying not to drive. The idea is not to drive the transmitter too hard. But you're right. I mean, the noise sidebands are just going to be, horrible. Yeah, I think you may be. Well, I've lost. I've partly retired, Anand. So you have to blame somebody else.
Sure. Okay, great. I think we have
the other thing which I noticed is, as many people have already mentioned, towards the south and southwest, that's all okay. But if you look towards the north, towards the North Sea, then you are in trouble because of the polar ionosphere.
Yeah, absolutely.
I think he did mention that your thing works best in the mid latitudes where the ionosphere is well behaved.
Britain being at the northern end of that mid latitude, more or less.
So actually,
towards the south.
Looking north, Anand, is just wouldn't it be nice? But it's always problematical looking north from with a radar. So like this. So yeah, lots of clutter, which of course is very interesting. I mean, you can use it for science. You can model. You can measure the position of the auroral oval and all those things. But yeah, for looking at as a radar for detection purposes, it's a bit of a challenge.
Yeah. Thanks.
Okay, great. Thanks. I think we have one last question. Mr. S. Sripati, please unmute yourself, turn on your camera, and go ahead.
Yes, thank you, Paul, for your talk.
Thank you.
Question is whether this 40H also can be used as an ionoson.
Will we be using an ionoson, did you say?
40H also can work as ionoson, or ionoson also can be used as 40H.
Sorry.
Ionoson can be used as OTH.
Ionoson can be used as OTH, did you say?
Yes.
OTHR,
yes.
he means.
He's asking.
OTHR.
No, because the ionoson is vertical.
We have many ionosons in India. Whether that can be used as a OTH.
Yeah. Okay. Right. Yes. Yeah. Sorry. There's some echo on the line. Yeah. No, you're dead. You're obviously dead right. So typically for an over the horizon radar, if you're going to look at, actually, if we look at John as a good example, the Australian system, they have a mini radar. They have a mini radar. Yeah, and they also have they also have vertical ionosons, and they have oblique ionosons. So, you know, they get VIs, vertical incidence ionograms, and they get OIs, oblique incidence ionograms. So, yeah, I mean, both of those things are important. So, I mean, we have an assimilative model at Birmingham, which starts off with a physics-based model of the ionosphere, and it takes in GNSS data to modify the physics-based model, you know, it does take in VIs and as well, perhaps not optimally, but you know what you really need is a system which takes in GNSS data, OIs, VIs, and backscatter ionograms, and brings them all in to the model, and then I'm going to say adjust the model, but you know, produces an optimal output, and that's what we will need for this system.
Thank you.
Okay.
I think
and another
question
is.
Yeah, please go ahead.
Yeah, sorry.
Yeah, another question is how this OTH is applicable for ionospheric research. You are talking about application of the OTH for detection of ships and aircrafts.
I'm using, so this over the horizon radar with this, I'm talking about it in terms of a, you know, a radio science project for, you know, I mean, it's a radar. This is a radar for detection of targets of one sort or another. It could be used for sea state modeling as well. But this is not for science. It's going to need science to
yes.
Need science to support it. Otherwise, you know, it won't work without good science supporting it.
Yeah, great. Thank you. I think we are already 2 hours into the program, and we would have to stop at some place. So well, being the moderator, I have the advantage of having the last word. So I get to ask just a couple of questions myself. The first question, Paul, is that you've talked about in order to do the coordination, that is radar range to ground range, you have to use not just the total electron content modeling, but the actual ionospheric profile modeling.
Yeah.
So, but given the large amount of GNSS observations available all across, and the data being networked almost in real time, isn't it possible to use that GNSS data of the ionosphere in real time in order to get an almost real-time ionosphere?
Yeah, no, it absolutely is. The problem comes when if we wanted to use it to look out over the sea, or
there are not many seaborne observations.
If we built this in the UK and if we pointed it towards Europe, I totally agree. We could do what you said because there's GNSS data streams everywhere. And in fact, they come in real time. They're fed into the University of Birmingham's InRaSS ionospheric modeling scheme, which you can find on the internet. And you can see the real-time ionospheres as a consequence. But it just depends. You know, we're trying to come up with an architecture that looks that could bring benefit and also would work at high. Could also work. It will work anywhere, basically, not just over Europe.
Thanks.
Or India. It would work. Yeah, but maybe it would work over India because you've got loads and loads of GNSS. receivers. So maybe we could even try it in India, and it would actually work there, even with the very difficult ionosphere you have there.
Yeah, I mean, in future, going forward, I mean, if you could visualize a situation where you don't need to model the ionosphere, so you really don't care about its vagaries, because you have real-time measurements.
Yeah.
With a large network of GNSS stations or whatever. Then this would be a perfectly suitable situation, right?
Yeah, no, it would. I mean, that's the engineering solution to a difficult science problem.
That's right. Well, finally, I think I'd lastly ask, what must have been in the mind of all of us, but we're afraid to ask, is you certainly are not doing this huge amount of research, spending such a huge amount of money to build over-the-horizon radars to track commercial aircrafts and ships, right? I mean, what is it basically aimed to detect? I mean, what is the primary purpose of this entire exercise?
I mean, it's all hypothetical at the moment, Amitabha, and so we will, we're hoping it may go somewhere, but we don't know. Lots of relatively basic engineering research here, and certainly lots of science research.
Okay. No, but basically what must be, I mean, it is certainly in my mind that, I mean, I really wouldn't want to spend so much of money and effort just to track commercial aircrafts traveling over the Atlantic.
Yeah.
Who cares?
Yeah. No,
right. Okay. So what you're saying is it has future possibilities.
Yeah, it has future possibilities. It's all hypothetical at the moment. Yeah.
Okay, great. Well, thanks again, Paul, for a wonderful lecture. I wish we could ask more questions, spend more time with you, but all good things must come to an end. So thank you once again. Now I'll hand over to Mr. N.K. Wadhwa, our former Scientist Forum Secretary, for a formal vote of thanks. Mr. Wadhwa, please.
Thank you, Paul.
Thank you, Dr. Sengupta ji, for providing me this opportunity to give vote of thanks. Dear Professor Dr. Venugopal Achanta ji, Dr. Paul S Cannon, Dr. S Ananthakrishnan, Dr. Amitabh Sengupta, Dr. Mr. R.V. Saxena, family members of late Dr. A.P. Mitra, colleagues from NPL, former Scientist Forum, and distinguished participants from InRaSS and abroad, respected colleagues, students, and everyone joining us online through WebEx or our YouTube channel. On behalf of organizing committee, we extend our gratitude to Professor Paul S Cannon from the University of Birmingham to thank you very much for agreeing us to deliver this 10th AP Mitra Memorial Lecture on short notice, and for your insightful presence of a new HF over the horizon radar architecture, this lecture. It was very informative. We are also deeply grateful to Professor Dr. Venugopal Achanta, Director of CSIR NPL, for presiding over today's event and sharing such encouraging word with us. We would also like to thank Dr. S. Ananthakrishnan, President of InRaSS and an esteemed radio astronomer, for his mentorship and support of the Radio Science Society. We are grateful to InRaSS for their partnership with CSIR NPL in organizing this event, and the dedicated team at both InRaSS and CSIR NPL, whose hard work has contributed immensely to today's success. I would also like to recognize Dr. Amitabh Sengupta, Chairman of the Dr. A.P. Mitra Memorial Lecture Committee, for his guidance and support in the logistics. Many thanks to Dr. J.C. Sharma, President of FSF, and Vice President of NPL FSF, Mr. Rajan Babu Saxena, who is also convener of this event, for his skillful coordination with various team and stakeholders. We appreciate Dr. Harikishan, Treasurer of NPL Forward Scientist Forum, for his detailed attention to the planning of this event. And thanks to our Joint Secretary, Mr. Anil Suri, for his assistance. A special thanks to family of the late Dr. A.P. Mitra, who honored us with their presence today. Their continued connection with NPL Former Scientist Forum since the start of this lecture series has been invaluable. Finally, thank you all, our distinguished guest participants and our online audience. Your presence reflects your respect and appreciation for Dr. A.P. Mitra's legacy. We look forward to seeing you all again next year. For update, I request you to please visit our website, that is www.nplfsf.in, in the last quarter of 2025. Thank you all. Thank you, everyone. Thank you.
Thank you.
Over to you.
Well, Amitabh, you need to...
Yeah. Thank you, Mr. Vatva, for the formal vote of thanks. So once again, thank you very much, Paul, for that wonderful lecture. And I thank all of you that participated. So now it's my pleasure to close the meeting. So thank you again and have a good evening.
Thank you very much. Nice seeing you all.
Bye.